Hi everyone, welcome to the Software Development Essentials Workshop and the third of 5 total classes. This class is the second of a 2-part series, the Full Stack Developer, and focuses on the back end. The first class in this series focused on the front end. This class is geared towards the following audience: entrepreneurs who are looking to build a software-backed product, professionals who either already find themselves in the technology space or are looking to break into it, students who are looking to learn some material they might not get in the classroom, and curious individuals who just want to understand more about how the modern world is being built. The objective of today's class is to continue diving into the stack and to focus on the components of and the interactions between the business logic layer and the data access layer, otherwise known as the backend. Today's schedule. We're going to jump right back into the stack and cover the backend and what it captures. We're going to cover databases, both relational and non-relational, services, and information security. Like the other classes, after the lecture, there will be a quiz waiting for you on the Teachable platform, if that's where you're watching this video. This is a picture of Simba cuddling with her pet squirrel. So, to begin, let's do a quick recap of the stack. A given web application consists of a set of functions working together in a defined architecture to deliver specified services to the user. The simplest application architecture, which we are covering in these classes, consists of 3 layers. First is a presentation layer. Presentation layer is what the client sees when they access the application through a website or a web-based application portal. We covered this in the last class. This is also referred to as the front end, comprised of HTML, CSS, JavaScript, and the relevant frameworks and libraries. It also involves the design, both the UI and the UX of the product being built. The second is the logic layer. The logic layer contains application logic and business rules that help fulfill application requests. This layer makes calculations and decisions about how to process requests while controlling the transmission of data between the data layer and the presentation layer. And lastly, the data layer. The data layer is a system that stores information and retrieves it to pass to the logic layer when it's necessary to complete a calculation or when it needs to be passed to the presentation layer, where it becomes visible to users. The sum of these layers is what is referred to as the stack. Today, we'll be diving into the other 2 layers that we haven't discussed yet, the business logic layer and the data access layer, together which comprise the backend. So what exactly is captured within the backend? If we remember from last class, web browsers communicate with web servers using the Hypertext Transfer Protocol, HTTP. When you go to any website, an HTTP request is sent from your browser to the target web server. Web servers then process these requests when they arrive and reply to the web browser with an HTTP response containing HTML, CSS, and JavaScript. Backend developers focus on the server side of the application, which is anything that the web server does to process these requests. This includes tasks like validating incoming requests. Does the user's request even make sense? Using databases to store and retrieve data. What raw data do I need to satisfy the user's request? Any subsequent business logic or data processing? How does this raw data need to be manipulated in order to satisfy what the user is asking for? And finally, constructing and sending the correct content to the client in an HTTP response. To use a car analogy again, the back end is the engine and the inner mechanics of your application, whereas the front end is the exterior and interior design of your application. If we remember, client-side code is written using HTML, CSS, and JavaScript. Server-side code, on the other hand, can be written in any number of programming languages, as long as the proper software is installed and available on the web server that the code is being run on. Examples of popular server-side web languages include PHP, Golang, Python, Ruby, C or C# or C++, and Java. Looking at the image on the top right here, what's highlighted in green, the structure, what elements are used, how they're ordered, that's all front end or client side, including the CSS and JavaScript that's not shown. The content that fills up the structure and how that content is generated, here Black Goose Bistro, that's determined by the server side or the back end. Let's use Airbnb again to illustrate this. The fonts, colors, layout, designs, etc. shown on this page constitute the front end of the page. The content, the listings themselves, are fetched from a database, processed, and returned to your browser. That data storage and processing is the back-end part of the application. So let's keep going with this Airbnb example. You enter a check-in date, a checkout date, number of guests, type of room, and price range into the form, and you hit enter. When you hit enter, the browser sends a request to the Airbnb web server saying, hey, I want all the listings that match this criteria. The web server then fetches all the information, including images, descriptions, prices, etc., sorts the listings based on price, populates an HTML template designed and created as part of the front-end development with all the information that it gathers, and returns that resulting HTML in an HTTP response to be rendered by your web server. That fetching from the databases, filtering by specific criteria, the ordering of the posts, the populating of the HTML template, and returning the HTTP response, all the work, that's done by the backend. So again, to really harp on this, because this distinction is really important, the client, your web server, is sending a request to the server. The code that is being rendered by the client, HTML, CSS, and JavaScript, is generated through client-side programming and represents the front end. Any code that is written on the server side to access data, transform the data, run calculations, and finally populate the frame that is your front-end code, that's the back end. Client-side programming, server-side programming, front-end, back-end. The appearance, the structure of your website, front-end. The content and inner workings of your website, back-end. Super important. Let's visualize this. The dotted line here represents the division between the front end and the back end. The left-hand side of this image should look familiar to us. A client, your web browser, makes an HTTP request to a web server, the front door of an application, which ultimately returns an HTTP response back to the client. This is what we covered in the last class. The right-hand side of this diagram, the databases which store the data, and the application server which the web server communicates with and which hosts services that transform from the databases and performs any other necessary business logic, is what we'll be covering today. One quick call out here before we dive into the backend is that it's totally feasible to have a website or an application that only has a front end. This is called a static website, one that only has HTML, CSS, and JavaScript. There's no calculations that need to be made or data that needs to be stored or anything else. So it doesn't even need an application server or any other backend components. It's just front-end content. So something like this history of our drive-through beer store website or isit2021yet.com website is just hard-coded static content. It can exist and function solely off of front-end code. But most websites are more complex and need more than just hard-coded front-end code. They need to access the databases, run some calculations, do some work, and then return the final HTML content back to the web server. It's those applications that require a backend. So let's start with databases. First off, what are they? Well, before we define databases, we have to define data quickly first. Data are a set of qualitative or quantitative values about one or more objects. For example, your name, age, height, weight, etc. are some pieces of data related to you. A picture, image, file, PDF, etc. can also be considered data. The address, stock ticker, and annual revenue are some pieces of data of a business. The name, city, record, and the number of championships are some pieces of data of a sports team. So there's an entity and there's characteristics or data about that entity. A database is an organized collection of data, typically stored electronically in a computer system. A database is usually controlled by a database management system known as a DBMS. Together, the data and the DBMS are referred to as a database system. This is a really important distinction. The database is the data store itself, and the DBMS is the thing that communicates and interacts with the database. Data within the most common types of databases, relational databases, which we'll get to in a second, in operation today are typically modeled in rows and columns in a series of tables to make processing and data querying efficient. The data can then be easily accessed, managed, modified, updated, controlled, and organized by the DBMS. So let's discuss a database example. An online registry of high-priority GoFundMe campaigns uses a database to store data about donation campaigns. their names, descriptions, fundraising goals, organizers, contributors, etc. Your bank uses a database to track all of its customers, their balances, their active credit cards, their transactions, their address, etc. Airbnb uses databases to store all of its available listings. The rows are listings and the columns are the address, the number of bedrooms, the ratings, the host, pictures, etc. We can provide a countless number of examples for the usage of databases. And again, while it's possible to have an application that doesn't require any sort of backend at all, most do. A common question when we start covering databases is, well, what's the difference between a database and a spreadsheet? It's a good question. Apart from the fact that databases aren't always rows and columns in a series of tables, we'll discuss this more in a bit, there's a few other things to note. Spreadsheets were designed for one user, and their characteristics reflect that. They're great for a single person or a small number of users, like in Google Sheets, who don't need to do a lot of incredibly complicated data manipulation. Databases, on the other hand, are designed to hold much larger collections of organized information, massive amounts at times. We're talking millions or billions or trillions of rows. Databases also allow multiple users at the same time to quickly and securely access and query the data using highly complex logic and language. Thousands of users using the Airbnb app will be hitting the same listings database. So you can use spreadsheets mentally to visualize how a table-based database looks internally, but remember, it's not that simple. So let's give this popular table-based form of databases, again, the most widely used type of database, a name, a relational database. Relational databases became dominant in the 1980s. Items in a relational database are organized as a set of tables with columns and rows. Relational database technology provides the most efficient and flexible way to access structured information. And structured is important here, as it'll help us distinguish between relational databases and other types of databases later on in the classes. An RDBMS, or Relational Database Management System, is a DBMS specifically designed for relational databases. Therefore, RDBMSs are a subset of DBMSs. While a relational database describes the type of database an RDBMS manages, the RDBMS itself refers to the database program. It's the software that executes queries on the data, including adding, updating, deleting, and searching for data. RDBMS is the most popular DBMS type in the market, which makes sense given that relational databases are the most widely used type of databases. Examples of RDBMS systems include names you may have heard of before: MySQL, Postgres, Oracle, and Microsoft SQL Server. So let's keep diving in and go over some aspects and attributes of relational databases before jumping into an example. First off, how does one interact and communicate with a relational database? We know that it's through RDBMS, but what language does the RDBMS use to do that? Many of you may have heard of this acronym before, but the answer is SQL. SQL. SQL, or Structured Query Language, is the primary interface used to communicate with the relational databases. Again, relational only. SQL became a standard of the American National Standards Institute in 1986, and the standard version of SQL is supported by all popular relational database engines. SQL is used to add, update, or delete rows of data, retrieve subsets of data for any subsequent transaction processing and analytics, and to manage all aspects of the relational database. When creating a relational database, you would first use SQL to establish a database schema, which is its structure as defined by what columns are required, which of those must be unique, otherwise known as a key, and which of those has a reference to a column in another table. So let's look at an example. It's a bit jarring to look at, in my opinion, but here we're using SQL to create a table called customers, which contains 5 columns: ID, name, age, address, and salary. That means that each row in this table will have all of these columns. You can also see here that the ID column is defined as a primary key, which means that no 2 rows in the table can have the same ID. This is very important. You can also see some other things going on. Like for each column, there's a data type. The ID is an integer. The name is a string of max length 20. The age is again an integer. The address is again a string, this time of max length 25, and salary is a decimal with 18 digits max before the decimal point and 2 digits max after the decimal point. Don't worry about the difference between CHAR and VAR CHAR. That's a bit too in the weeds, but they're both strings is the takeaway, which is text. You can also see some constraints on some of the fields. The ID, name, and age fields in any given row cannot be null. Null means empty. They must be provided. On the other hand, a row may exist where a customer doesn't have a recorded salary. That's not a mandatory column. And so this introduces some more aspects of relational databases. The first is data integrity, which is the overall completeness, accuracy, and consistency of data. Relational databases use a set of constraints to enforce data integrity in the database. These include primary keys and other constraints, such as the not null constraint. These integrity constraints help enforce business rules on data in the tables to ensure the accuracy and reliability of the data. Put another way, constraints enforce rules that ensure the data within a given table is consistent structurally. Every row must have a name. Another aspect is a database transaction, which is one or more SQL statements that are executed as a sequence of operations that form a single logical unit of work. Transactions provide an all or nothing proposition, meaning that the entire transaction must complete as a single unit of work and be written to the database, or none of the individual components of the transaction should go through. In the relational database terminology, a transaction results in a commit or a rollback. There's no in between, and we'll look at an example of this in just a second. And finally, each transaction is treated in a coherent and reliable way independent of other transactions. So one transaction succeeding or failing should have no impact on any other transaction succeeding or failing. And finally, one level deeper, the aspects we just covered can all be captured in something known as ACID compliance. All database transactions must be atomic, consistent, isolated, and durable to ensure data integrity. So what do each of those mean? Atomicity is that all or nothing proposition that we just talked about. It requires that either the entire transaction be successful or it should be entirely invalidated. Consistency is the constraints we just talked about. It mandates the data to the database. It mandates the data written to the database as part of any transaction must adhere to all the rules and constraints defined in the database schema. Isolation is that independence thing we just talked about. It requires each transaction is independent unto itself. Isolation ensures that concurrent execution, which means two transactions hitting the database at the exact same time, concurrent execution of transactions leaves the database in the same state that it would have been if the transactions were executed sequentially, let's say minutes or hours apart. And finally, durability mandates that a committed transaction, that's a transaction that has succeeded, will remain committed even in the case of a system failure. So once it's been committed, it stays committed. All right, so let's go back to the table we defined before and run through some basic CRUD, create, update, and delete operations. So again, here we view SQL to create a table called customers. Customers has 5 columns: ID, name, age, address, and salary. It defines that the ID column is the primary key, and therefore that means that no 2 rows in the table can have the same ID. It also has some other constraints to guarantee consistency. It says that the ID, name, and age fields cannot be null. In other words, they must have values specified. So a row cannot exist in the table that doesn't have an ID, a name, or an age. Think of this like the asterisked fields on a form you're filling out. These fields are mandatory and must be provided. This ensures data integrity. So now here we have 6 separate SQL operations. Each one is adding a new row into the customer's table. Looking at the first one, we can go through each word. Insert, that's the operation. We're inserting a row into the table. Into the table, customers, which is the name of the table. Then specifies between parentheses all the columns for whose values there are about to be specified. So ID, name, age, address, and salary. And then finally, the word values followed by another set of parentheses, which specify the values for each of those columns. So the ID is 1, the name is Ramesh, the age is 32, the address is Ahmedabad, and the salary is 2,000. And you can see each block of 2 lines below that is just adding another customer into the table. And one thing to call out here is you can see that no 2 rows have the same ID. They increment by 1 each time because the ID has to be unique within the table. So after those statements are executed, the table will look like it does here. So you can see it's got the 6 rows. It has the 5 columns, ID, name, age, address, and salary, and it has all the values that were specified in the insert statements from the previous slide. Next, let's do a read operation from the table. Here, we want to fetch all the rows in which salary is greater than 2,000. And for those rows that we fetch, we want to read specifically the ID, name, and the salary fields. So again, the block on the top here, we're saying we want to select, and then we specify the names of the columns, ID, name, and salary, from the name of the table, customers, and then we provide this condition where salary is greater than 2,000. The result of this operation will fetch the 3 rows that match the salary condition, as well as the columns that we requested for within those rows. And you can see that in the image on the bottom. Here we fetched 3 rows for IDs 4, 5, and 6, Chaitali, Hardik, and Komal, and their salaries. And you can also see their salaries are greater than 2,000, which was the condition. Next, we want to update the customers table. We want to find the row that has an ID of 6, and we want to change the address to Pune, which is actually the city I was born in, so shout out to Patrakar Nagar. Once we've run that operation, the table will be updated and look like the below. You can see Komal's address has been changed to Pune. And so again, going through the command, we want to update, that's the first word, the customers table, which is the name of the table, where we want to set the address, which is the name of the column, equal to the word Pune, where, that's the condition, the ID of the row in question is 6. So we want to take the row that has ID 6 and change the address column within that row to be something different. Next, we'll do a quick delete operation. Here, we're finding all customers who have an age of 25 and deleting those rows from the table. So here, we would expect that rows 2 and 4 would be deleted from the table, which is what we see in the resulting output. So again, let's look at that command. Delete is the operation from the customers table, and then the condition is where age equals 25. And then the 2 images on the bottom show the before and after states of that table. You can see in the before state, both Kilan and Chaitali, who have ages of 25, are in the table. And after the delete operation, you can see that their rows are no longer present. So in this example, let's say that row 2 was deleted, but before row 4 was deleted, there was a massive power outage or some other failure. The all or nothing proposition that we talked about before, atomicity, would mean that this transaction would be rolled back. So both rows 2 and 4 would still be in the table. Remember, either the entire transaction succeeds, which means both rows are deleted successfully, or none of it does. Similarly, if the transaction did go through completely and there was a massive power outage when the power was back, the table would look like it did after the deletion. This is durability. Once the transaction is committed, it remains committed no matter what happens afterwards. So to recap relational databases, items in a relational database are organized as a set of tables with columns and rows. An RDBMS, a relational database management system, is the software that executes queries on the data. SQL, structured query language, is the primary programming language used to communicate with the relational databases. And all database transactions must be ACID compliant. Atomic, meaning a transaction is all or nothing. Consistent, meaning all rows comply with the constraints and requirements of the original table schema. Isolated, meaning that transactions are independent of one another. And durable, once a transaction succeeds, it's there forever. But as we said earlier, not all databases need to follow this row, column, table structure. In other words, not all databases are relational databases. Non-relational databases, also referred to as NoSQL databases, emerged as a popular alternative to relational databases as web applications became increasingly complex. NoSQL/non-relational databases can take a variety of forms, but in general, they are more forgiving in their structure and form than relational databases are. The critical difference on this thread between NoSQL and relational databases is that RDBMS schemas rigidly define how all data inserted into the database must be typed and composed through the constraints and the schema that we saw before, whereas NoSQL databases can be schema agnostic, allowing unstructured and semi-structured data to be stored and manipulated. We saw before that the customers table had these columns and these constraints, and this is the primary ID column, so on and so forth. All of those constitute a schema for the table, which NoSQL tables do not have. Within non-relational databases, there are different types. We're going to cover 5 of them here at a high level: key value stores, columnar stores, document stores, graph databases, and search engines. Key value databases store and provide simple knowledge regarding key value pairs. Document databases are schema-free systems that store data in the form of JSON documents, also using key value pairs. Search databases are similar to document stores, but are optimized for retrieval of data on complex criteria. And columnar databases are optimized for fast retrieval of columns of data as opposed to rows. Finally, graph databases make it easy to build applications that work with highly connected datasets. We're going to jump into each one of those. So starting with a key value database. A key value database stores data as a collection of key value pairs in which a key serves as a unique identifier. So it's kind of similar to relational in that there's a unique key associated with each row, but it's different in that you don't have a set number of predefined columns. There's always just one, the value, and that can contain anything. It isn't restricted by any constraints. In fact, both the keys and the values can be anything, as long as the keys remain unique. The simplicity of key value stores makes them well suited to databases where the stored data is not particularly complex and speed is of paramount importance. When we talk about speed, we're talking about how fast we can access the data associated with a given key. So again, instead of rows with some number of predefined columns, all you have here is a single key that maps to a single value. When you're reading from the database, you say, hey, give me the value for this key or that key, and you'll get it back. So again, it's very simple. So maybe you have a classroom assignment where every student can either submit a journal or a picture or a number or a book or a painting that they most strongly resonate with. Then the key Darrell Rivas, a student, will return whatever file Darrell has submitted. Something like that might be a good use case for a NoSQL database. Or you could have a single table that holds users, transactions, and products all in one database. The keys could be the name of a user, the ISBN of a product, or the confirmation code of the transaction, and the values could be all the information about each respective entity. All these things could exist in a single NoSQL database, which is schema agnostic. Compare this to 3 separate relational databases, one for users, one for transactions, and one for products, each with a predefined schema. Moving on to the next one. A document database stores and queries data as JSON documents. It's actually pretty similar to key value database, except that now the value for a given key is a JSON document. Well, it's JSON. JSON is a lightweight format for storing and transporting data, itself using key value pairs. So it's inception with key value pairs. A key gives you access to a document, which itself contains many key value pairs. Where does it all end? The document model works well with use cases such as catalogs, user profiles, and order management systems, where each document is unique and evolves over time. So in this example, the database records transactions on a retail website. Since a transaction can contain a variable number of items, the transaction record is just stored as a single JSON document, And the key here might be like a transaction ID, which is unique. You can see how the shape of the document varies, but because it's a non-relational database, that's okay. Moving on, a search engine database is dedicated to the searching of data content. Search engine databases are similar to document databases, but have the added benefit of using indexes to categorize the similar characteristics among data and facilitate search capabilities. Search engine databases are optimized for dealing with data that may be long, semi-structured, or unstructured, and they typically offer specialized methods such as full-text search, complex search expressions, and the ranking of search results. So, let's say you were uploading 3 documents to your search database. The documents are each sentences, but you can imagine them being larger than that. Let's say complete articles published on NewYorkTimes.com. Each article is uploaded to the database with a unique key, similar to a document database or a key value database. After this point, though, is when the search database differentiates itself by creating what's called an inverted index, which is a separate table that tracks terms. So the word butterfly or sky or wind, and literally every other word that appears in any of the articles, with the exception of the words that are in the stop word list, which are more common words, articles, the, one. Now, when a user goes to NewYorkTimes.com and in the search bar at the top searches for the word butterfly and expects to find all the relevant articles about butterflies, the search database can quickly look at the inverted index and figure out which articles contain that word, so they can be returned to the user. This, as opposed to looking through each article in real time and searching the full text of each article for the word butterfly. Instead, when the article is uploaded to the search database, the inverted index is also updated to contain the words and map them to article numbers or article links. You can see how the performance of one is much better than the other. So again, search databases are used for searching, specifically on possibly complex search criteria and long unstructured data. Moving on, a columnar database is optimized for fast retrieval of columns of data as opposed to rows of data. You can think of this as an inverted relational database. So you still have rows and columns, except now you're going to be fetching columns in their entirety, not rows in their entirety. Well, why would you want to do this? The primary benefit you can get by storing data in a columnar database is that some of your queries could become really fast. And a columnar database is preferred for analytical applications because it allows for fast retrieval of columns of data. They're designed for data warehousing and big data processing. So let's say you have an analytics application, which really doesn't care about individual items in your catalog, but rather only cares about the average price or average size across all the items in your catalog. Using a standard relational database, you'd have to read every single row, fetch the price field, and then calculate the average across all those rows. Or you could just use a columnar store and just fetch the price column directly and find the average on that column. The latter is much faster. That's a use case where maybe you prefer to have a columnar store, where it's not about the individual items, the rows, as much as it is about the holistic view of each individual metric, the columns. And finally, a graph database is purpose-built to store and navigate relationships. Graph databases use nodes to store data entities and edges to store relationships between those entities. Graph databases have advantages for use cases such as social networking, recommendation engines, and fraud detection, when you need to create relationships between data and quickly query these relationships. So this is Instagram or Facebook or LinkedIn. You want to see all the mutual friends you and Howard Shore share, or you just want to see all the people who follow Lady Gaga, etc. That sort of relationship data is often stored in and then retrieved from a graph database. So a lot of times the question then becomes, when should you use a relational database versus a non-relational one? And as I've answered before for a different question, it depends. You should use a relational database if asset compliance is a top priority or a requirement. You would use relational databases if you have a rigid structure or schema, and if you want to make sure all data follows that schema. On the other hand, you would use a non-relational database if your input data is particularly heterogeneous and difficult to capture with a normalization schema. You would use a relational database if your use case is strongly consistent online transaction processing. You would use a non-relational database if your use case is more analytics performed on semi-structured or unstructured data. Short answer is it depends, and you can mix and match. You can use a relational database to store basic information about your students, a key value database to store all their homework submissions in various formats, and a graph database to store information about their relationships with other students. You can combine the queries from those databases and do whatever you need with them. Another common question in identifying which database to use is, which will optimize for speed of operations given what your use case is? The faster, the better. Just to give you a sense of the current landscape, relational databases make up the vast majority of use cases. That said, non-relational databases have become a lot more common just because of how complicated and nuanced data these days can be, which in turn makes the more flexible non-relational option preferable. The greater the unknown and variability you introduce in your data, the more likely you are to use non-relational databases. So you can kind of see that non-relational databases make up a larger share of the pie in 2018 than they did in 2013. Okay, so now hopefully we understand what databases are and how they can both be written to and read from, at least at a high level. There are DBMSs that sit on top of actual databases, whether they're relational or not, that allow us to extract data from them and write data to them. But what's actually orchestrating the reading and writing? Who is using the DBMSs? This is where we move on to the piece of this picture that we haven't gotten to yet, the application server, which houses the application that maintains and contains all the services that access data, transform it, run calculations, and finally, populate the HTML frame that is your front-end code that's returned in your HTTP response. On a conceptual level, a service is a software component provided through a network-accessible endpoint. The web server, which receives an HTTP request, communicates with the application server to perform tasks. So a user makes a request to the Airbnb web server saying, hey, I want all the listings within a 20-mile radius of Phoenix, Arizona. The web server says, okay, I need help with this, so it passes along a request to the application server. The web server and the service provider then use messages to exchange request and response information in the form of self-containing documents that make very few assumptions about the technological capabilities of the consumer. Put another way, the caller of the service and the service itself agree upon a contract of how the caller will request data and how the receiver will send back data. The rest is hidden, making it so that the service itself can be built using a myriad of technologies and programming languages, dealer's choice. But at the end of the day, the messages have to be transformed into a common format that can be consumed by any caller. It's very analogous to HTTP requests and responses between the client and the web server, except there are different protocols at play here. SOAP, S-O-A-P, and REST, R-E-S-T, are two of the big ones here if you want to dive into this further on your own, but we're not going to dive that deep here. All you need to know is that there's a contract in place for how services interact, both with one another and with the web server that calls them. We're going to take a look at two different architectures here and how to build services, a monolithic service and microservices. So just to ground us again, as we've been discussing, applications are often built in three main parts. A client-side user interface consisting of HTML pages and JavaScript and CSS running in a browser on the user's machine, a database layer consisting of many tables inserted into a common and usually relational database management system, and a server-side application. The server-side application, which runs on the application server, will receive HTTP requests from the web server, the front door, execute domain and business logic, retrieve and update data from the databases, and select and populate HTML views to be sent to the browser, the web browser, and ultimately the client. This server-side application can be a monolith, a single logical collection of code. Such a monolithic service is a natural way to approach building an application. All your logic for handling a request runs in a single process and in a single place, allowing you to use the features of a single programming language to divide up the application into its various functions. So to illustrate, let's go back to one of our example applications with Airbnb. There's the search results page, which, for a given set of criteria, we want to see all the corresponding housing options. So we input a bunch of things like dates, area, number of guests, and shoot off that request to the Airbnb web server. So an HTTP request goes to the Airbnb web server saying, hey, I need all the listings associated with all of these input criteria. The web server says, great, the request looks fine, and forwards that request to Airbnb's application service. The monolithic service then fetches all the relevant listings from its listings database, filtered based on the input criteria. It then combines that information into the HTML frame that we have, and then returns that package of data to the web server in an HTTP response. Alternatively, a user clicks on a given host to see more information about the host on a separate detail page. So an HTTP request goes to the Airbnb web server saying, hey, I need all the information associated with this specific host. It's a different set of data. It's a different request. The web server, though, says, great, the request looks fine, and forwards the request to Airbnb's single application service. The monolithic service then fetches all the relevant information about the host from its host database, combines that information into the HTML frame that we have, and then returns that package to the web server in an HTTP response. That's the monolithic version. A single monolithic service interacting with multiple databases, doing all the work, and returning the resulting dataset to the web server. Regardless of what type of HTTP request comes in, a single application will handle the request. Monolithic applications can be successful, but increasingly people are moving away from them, and it's considered bad system design. As you might be able to see, change cycles are very closely tied together. A change made to a small part of the application, let's say you want to show a host's email address now as well on their host page, which wasn't there in the past. So the service now also needs to read that field from the host database. That small change requires the entire monolithic service to be rebuilt and updated. Over time, as the application grows, it's often hard to keep a good structure within a monolithic architecture, making it harder to keep changes that ought to only affect one part of the monolith. It's like if renovating a single corner of your kitchen required to rebuild your entire home. And so now let's introduce microservices. The server-side application, as opposed to being a monolith, can also be built as a suite of individual microservices. It entails multiple logical executables that are each independently deployable and can interact with one another using a common protocol. As well as the fact that services are independently deployable and scalable, each service also provides a firm modular boundary, even allowing for different microservices to be written in different programming languages. They can also be managed by different teams. As long as they have contracts in place for how they're going to interact with one another when they have to, we're good. So now that the application is decomposed into multiple services, you can expect many single service changes to only require that specific service to be rebuilt. Now I can improve my kitchen without having to touch the rest of my house. So to illustrate, let's go back to one of our example applications with Airbnb. There's a search results page, which, for a given set of criteria, we want to see all the corresponding housing options. So we input a bunch of things like data, date, area, number of guests, and shoot off that request to the Airbnb web server. So an HTTP request goes to the Airbnb web server saying, hey, I need all the listings associated with all of these input criteria. The web server says, great, the request looks fine, and forwards that request to Airbnb's application service. The main application service receives the request and says, great, based on the information you're requesting, we need some help from the listing service, and so forwards the request along there. The listing service then fetches all the relevant listings from its listings database, filtered based on the input criteria. It then passes that information back to the main application service, that information is then put into the HTML frame that we have, and then is returned as a package to the web server in an HTTP response. Alternatively, a user clicks on a given host to see more information about the host on a separate detail page. So again, an HTTP response goes to the Airbnb web server saying, hey, I need all the information associated with the specified host. The web server says, great, the request looks fine, and forwards that request to Airbnb's application service. The main application service receives the request and says, great, based on the information you're requesting now, we need some help from the host service, and so forwards the request along there. The host service then fetches all the relevant information from the host database, passes the information back to the main application service, which populates the HTML frame that we have for the host page, and then returns that package to the web server in an HTTP response. In other words, microservices allow large systems to be built up from a number of collaborating components. So let's walk through some more visuals and examples to illustrate this. All right, so here let's start by taking a look at the image on the top left, which shows a monolithic service that contains 5 different pieces of functionality, denoted here by funny multicolored shapes. We have the orange Africa, the pink bow tie, the teal UFO, the magenta egg, and the green diamond. Each is a different piece of functionality. From the Airbnb example, think listings, hosts, users, payment, and messaging. But all are housed within a single monolithic service. The image on the top right shows a more microservices architecture, in which each piece of functionality has its own service. The bottom images are something we haven't really discussed yet and won't discuss in depth until next class, but as an intro, application servers aren't singular most of the time. Rather, you would copy your services across multiple servers so as to distribute traffic across multiple machines. With just that level of detail, you can see an added benefit of the microservices approach. Instead of copying the entire monolithic service over and over again across multiple servers, you can copy individual microservices across servers based on how much they individually get used. So if the orange Africa service gets used more often than the pink bowtie service, you can have it copied more times across servers. Alternatively, with the monolithic model, you just have to copy the entire thing, which is super inefficient, both in terms of cost and performance. But we'll get to more of that in the next class. Here, you can see how an online shopping application, think Amazon, can distribute its services. You have one service for anything related to accounts, one for anything related to viewing the product catalog, and one for placing and tracking orders. You can see that each service interacts with its own smaller set of databases, and that there's an orchestration service, the online shopping service, which sits above all the individual microservices. Again, remember the point here is that as long as there are contracts in place between the services as to how data will be requested and how responses will be returned, these individual services exist as completely independent entities. Can be written in different programming languages and can interact with different types of databases. Here's another example that takes it even further. On the left, you can see an application that is more monolithic in nature. It contains 3 total services, one for service scheduling, one for order processing, and one for account management. These in turn each interact with many of the databases. But you can see that each big service actually does have a lot of the same things. The service scheduling service and order processing service both check customer status and determine product availability as functions. In a monolithic model, this would mean that whatever code is responsible for those 2 operations would be copied and would exist in both services. Same thing goes with the order status code. Alternatively, on the right-hand side, you can see these 3 larger services broken even further into the specific operations they contain. So now there's a check customer status service that is shared between the service scheduling and order processing service, and a check order status service that is shared between the order processing and account management services. This microservices architecture removes any code duplication, as shared activities are broken out into their own services, which can be called by whoever needs them. Remember how we learned about functions in class number 1? This is closely tied to that. All this to say, even though in the left side model there are 3 services, it's still more of a monolithic model. A monolith indicates that the application can be broken down even further, and a true microservices architecture entails getting down to really small, isolated pieces of functionality that can then be shared and reused by different parts of the application. So break things down and then break them down again, and keep going until 0 code duplication is occurring in your application. For as long as we've been involved in the software industry, there's been a desire to build systems by plugging together components, much in the same way we see things are made in the physical world. When talking about components, we run into the difficult definition, though, of what makes a component. How exactly do we divide this monolith into parts? Along what lines? Our definition is that a component is a unit of software that is independently replaceable and upgradable. Looking at this more organizationally, Conway's law states that any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. When looking to split a large application into parts, often management focuses on the technology layer, leading to UI teams, server-side logic teams, and database teams. When teams are separated along these lines, though, even simple changes can lead to cross-team projects taking time and budgetary approval. So instead of this, the microservices approach to division is different, splitting up the services organized around business function. Such services take a broad stack implementation of software for that business area, including user interface, persistent storage, and the service implementations. Consequently, the teams are cross-functional, including the full range of skills required for the development of that given service: user experience, UI, database, services, management. One company organized in this way is Ridgeline, the company I currently work for. Each product area, which constitutes a different part of the application, has engineers, designers, QA, security, and management. Cross-functional teams are responsible for building and operating each product, and each product is split out into a number of individual services communicating via a message bus. Large monolithic applications can always be modularized around business capabilities too, although that's not the common case. So now you have your databases in place to store your data, services to access and do work on that data, and a front end to render the final client-side code. That is the stack in a nutshell. Congrats. Again, just going to keep showing this image because it's really important. And to differentiate between a monolith and a microservices approach, the image on the bottom shows that. The approach on the left is identical to the image on top. It is a monolith. Alternatively, the image on the right shows a microservices approach. Web server goes to a single orchestrating server initially, which then fans out to all the various functions in the application, each of which has its own database. The orchestrator then interacts with whatever microservices it needs to, combines the responses, packs it all up, and returns a response to the client. So now let's move on to a different topic, which is also so important in the field of software development, especially in this day and age: information security. How do you secure all this data you've set up so well? Information security is basically the practice of preventing unauthorized access, use, disclosure, disruption, modification, inspection, recording, or destruction of information. Information can be anything like your details, or we can say your profile on social media, your data in a mobile phone, your biometrics, etc. Thus, information security spans so many research areas like cryptography, mobile computing, cyber forensics, online social media, etc. Information security programs are built around three objectives, commonly known as CIA: confidentiality, integrity, and availability. Confidentiality is perhaps the element of the triad that most immediately comes to mind when you think of information security. Data is confidential when only those who are authorized to access it can do so. To ensure confidentiality, you need to be able to identify who is trying to access data and block attempts by those without authorization. Passwords, encryption, authentication, and defense against penetration attacks are all techniques designed to ensure confidentiality. Integrity means maintaining data in its correct state and preventing it from being improperly modified, either by accident or maliciously. Many of the techniques that ensure confidentiality will also protect data integrity. After all, a hacker can't change data they can't access. But there are other tools that help provide a defense of integrity in depth. Checksums can help you verify data integrity, for instance, and version control software and frequent backups can help you restore data to a correct state if you need to. Availability is the mirror image of confidentiality. While you need to make sure that your data can't be accessed by unauthorized users, you also need to ensure that it can be accessed by those who have the proper permissions. Ensuring data availability means matching network and computing resources to the volume of data access you expect, and implementing a good backup policy for disaster recovery purposes. The field of information security has grown and evolved significantly in recent years. It offers many areas for specialization, including securing networks and infrastructure, securing applications and databases, security testing, information systems auditing, business continuity planning, the list goes on. So those are some common philosophies related to information security. But now let's dive into some relevant subjects within the field of information security. First off, we're going to start with authentication and authorization. Authentication and authorization might sound familiar, but they are distinct security processes in the world of identity and access management, otherwise known as IAM. Authentication confirms that users are who they say they are. Authorization gives those users permission to access a resource. So starting with authentication. Authentication is the act of validating that users are whom they claim to be. This is the first step in any security process. This is logging in. So you would complete an authentication process through passwords. Usernames and passwords are the most common authentication factors. If a user enters the correct data, the system assumes the identity is valid and grants access. One-time PINs grant access for only one session or transaction. Authentication apps generate security codes via an outside party that grants access, or biometrics. User presents a fingerprint or an eye scan to gain access to the system. In some instances, systems require the successful verification of more than one factor before granting access. This multi-factor authentication, MFA, requirement is often deployed to increase security beyond what passwords alone can provide. Authorization, on the other hand, is the process of giving the authenticated user permission to access a specific resource or function within the application. This term is often used interchangeably with access control or client privilege. So once a user logs in, what parts of the application can they access? For Airbnb, can someone who logs in as a guest be able to edit or modify listings? Or should that only be reserved for someone who logs in as a host? Creating these divisions of function within an application is known as authorization. In secure environments, authorization must always follow authentication. Users should first prove that their identities are genuine before an organization's administrators grant them access to any resources. So just to keep diving into this, understanding the difference between the two is key to successfully implementing an IAM, Identity Access Management, solution. So let's use an analogy to outline the differences. Consider a person walking up to a locked door to provide care to a pet while the family is away on vacation. That person needs authentication in the form of a key. The lock on the door only grants access to someone with the correct key in much the same way that a system only grants access to users who have the correct credentials. Authorization is in the form of permissions. Once inside, the person has the authorization to access the kitchen and open the cupboard that holds the pet food. The person does not have permission to go into the master bedroom for a quick nap, nor are they allowed to use the bathroom that's attached to the master bedroom. So authentication and authorization work together in this example. A pet sitter has the right to enter the house, authentication, and once there, they only have access to certain areas, authorization. Systems implement these concepts in the same way, so it's crucial that IAM administrators understand how to utilize both. Authentication. Let every staff member access your workplace systems if they provide the right credentials in response to your chosen authentication requirements. Authorization. Grant permission to department-specific files and reserve access to confidential data such as financial information as needed. Ensure that employees have access to the files they need to do their jobs, but not more than that. Understand the difference between authentication and authorization, and implement IAM solutions that have strong support for both. You'll protect your organization against data breaches and enable your workforce to be more productive. And this table just recaps the differences between the two, which you can read through quickly. Now let's move on to another topic in the field of information security, which helps guarantee confidentiality, and that's encryption. Encryption is the practice of scrambling information in a way that only someone with a corresponding key can unscramble and read. Encryption is a two-way function. When you encrypt something, you're doing so with the intention of decrypting it later. To encrypt data, you use something called a cipher, which is an algorithm, #algorithms. If we remember, nothing more than a series of well-defined steps that can be followed procedurally to encrypt and decrypt information. The algorithm can also be called the encryption key. Let's take a look at encryption using a simple cipher. One of the first use cases of encryption we saw as a society goes all the way back to Julius Caesar, who used a simple cipher to encrypt any messages he was sending to his generals out in the field or politicians in the government, where secrecy was of utmost importance. So for any message, Caesar used a monoalphabetic shift cipher that simply replaces each letter with one that is sequentially n places ahead of it in the alphabet. Obviously, we've come a long way since the early days, and our ciphers today are much more complicated, but just focus on the general concept. The sentence in its raw form is in plain text, it's unformatted, and it's unencrypted. That's the state it will return to once it has been decrypted. So let's go with the sentence, I had the best time with you today. I'm going to apply a monoalphabetic shift cipher of 3, which is the encryption algorithm / key, and turn that sentence into a ciphertext. So I had the best time with you today becomes LKDGWKHEHVWLPHZLWKBRXWRGDB. So, provided I've shared the key with the recipient, he or she could now use the same key, in this case the inverse of the algorithm that was used for encryption, to decrypt this message and read it. Again, obviously, the ciphers we use in digital encryption are much more complex, but the point is to understand the general concept behind it. You have something you want to encrypt, so you apply some algorithm to it to encrypt it. You then send the encrypted message along to the recipient, who then decrypts the message on the receiving end using the inverse of that algorithm. So we took each letter and shifted it three letters ahead, and then when it's decrypted, you would shift it 3 letters back. So let's go over some different types of ciphers. Shift ciphers, like the example we discussed above, 2 parties determine a number between 1 and 25 and shift the letters that number of spaces in the alphabet. The shift number serves as the encryption key. Substitution ciphers. These ciphers are plain text with ciphertext using an algorithm that is a fixed system. The encryption key is the document that shows the fixed system, which can be used to reverse engineer the encryption. So all instances of the word war become peace, and all instances of the word attack become retreat, so on and so forth. Transposition ciphers. This algorithm uses a set of rules, which serve as the key to change the order of the text into a different permutation that can then be encrypted. So, first word becomes second to last word, second word becomes last word, whatever it is. The key here is this map of starting place to resulting place, which serves as the encryption key. So instead of shifting each letter, here you're changing the order of the words, and your key becomes the guide as to how that order has been changed. Polyalphabetic ciphers. These are a type of substitution cipher that use multiple alphabets to further complicate unauthorized decryption of the ciphertext. Before we can talk about modern encryption ciphers, we need to also talk about public versus private keys. All the examples that we just went over are what we call private key cryptography, in which encryption is entirely contingent upon a single private key, which has to be exchanged between the sender and the receiver in order for decryption to take place. You can imagine how having this private key compromised can be disastrous, and therefore having to pass the key along with your message is quite a risk. Today, we can also practice public key cryptography. With public key cryptography, a public key is used to encrypt, and another separate private key is used to decrypt. Today, the most common forms of encryption are either public key or private key encryption. So public key cryptography can seem complex initially. Fortunately, a writer named Panayotis Vrionis came up with an analogy that roughly goes as follows. Imagine a trunk with a lock that 2 people, Bob and Alice, use to ship documents back and forth. A typical lock only has 2 states, locked and unlocked. Anyone with a copy of the key can unlock the trunk if it's locked, and vice versa. When Bob locks the trunk and sends it to Alice, he knows that Alice can use her copy of the key to unlock the trunk. This is essentially how what's known as symmetric cryptography or private key cryptography works. One secret key is used for both encrypting and decrypting, and both sides of the conversation use the same key. Now, imagine instead that Bob makes a trunk with a special kind of lock. This lock has 3 states instead of 2. It has state A, which is locked. The key is turned all the way to the left. B is unlocked, in the middle. And C is locked again, but this time the key is turned all the way to the right. Instead of one key, two keys go with this lock. Key number 1 can only turn to the left, and key number 2 can only turn to the right. This means that if the trunk is locked and the key is turned to position A, only key number 2 can unlock it by turning right to position B. If the trunk is locked in position C, only key number 1 can unlock it by turning the lock left to position B. In other words, either key can lock the trunk, but once it is locked, only the other key can unlock it. So now let's say Bob makes a few dozen copies of the key number 2, the key that only turns right, and shares them with everyone he knows and anyone who wants a copy, making it his public key. He keeps key number 1 for himself. It's his private key. So what does this actually accomplish? It means that anyone with key number 2 can send Bob a message, but only Bob can read that message since he's the only one with key number 1. Now, Bob doesn't have to share his private key with anyone, or he doesn't have to get it duplicated. He just needs to distribute the public key so that anyone can encrypt something and send it to him, and then only he can decrypt it. Looking at that in another way, you can see that with symmetric or private key encryption on the top image, a single key encrypts and decrypts, whereas in asymmetric or public key encryption, one key is used to encrypt and another key is used to decrypt. For those wondering if it's possible to just take the public key, find its algorithm, and then use the inverse of that algorithm to generate the private key, it's not possible, because a public key is calculated from the private key using something called elliptic curve multiplication, which is a mathematical formula that can only be calculated in one direction. So if this is the algorithm used to encrypt, it cannot be reverse engineered to decrypt. Someone must already know specifically what the private key is in order to decrypt it. So now that we've covered the differences between symmetric and asymmetric encryption, here's two examples of modern encryption algorithms, one of which is symmetric and one of which is asymmetric. So AES stands for Advanced Encryption Standard. It's a specification for encryption published by the National Institute for Standards and Technology back in 2001. It puts plain text through a number of transformation rounds determined by the key size, and each round consists of several processing steps. Let's not get too far into the weeds on this one, but the key length you can generate is between 128 and 512 bits long. RSA, on the other hand, stands for Rivas Shamir Edelman, after its creators, and it's a public key encryption algorithm that has been around since 1978 and is still widely used today. It uses the factorization of prime numbers to encrypt plain text. The one important takeaway here is that symmetric cryptography is much faster than asymmetric cryptography because of the mathematical complexity involved in asymmetric encryption. So symmetric encryption typically gets used when speed is the priority over increased security, keeping in mind that encrypting a message with a single private key still offers a high level of security. Private key encryption algorithms are really hard to crack, and when they are, they're generally retired. Example use cases of symmetric encryption include banking. Symmetric cryptography is typically used for bulk encryption of large amounts of data, including transaction data, credit card data, and other personally identifiable information, known as PII. It's also used in database storage more broadly, encrypting data at rest, which means not actively moving from one place to the other. If it's not moving, it's not as vulnerable to attack, so symmetric encryption is probably good enough, as long as the key is also kept safe on site. Subsequently, asymmetric encryption typically gets used when increased security is the priority over speed, and when identity verification is required. Example use cases for this include digital signatures, confirming your identity for someone to sign a document, and in the blockchain, confirming identity to authorize transactions for cryptocurrency. Moving on to another topic in the domain of information security, hashing, which is used to enforce the principle of data integrity. Hashing is the practice of using an algorithm to map data of any size to a fixed length. This resulting output is called a hash value, or sometimes called the hash code or a hash sum. Whereas encryption is a two-way function in which something is encrypted to be later decrypted, hashing is a one-way function. While it's technically possible to reverse hash something, the computing power required makes it very unfeasible. Hashing is one way. Now, whereas encryption is meant to protect data as it changes hands, hashing is meant to verify that a file or piece of data has been altered since it was hashed, that it is authentic. In other words, it serves as a checksum. Each hashing algorithm outputs at a fixed length. So for instance, you may hear about SHA-256, which means that the algorithm is going to output a hash value that is 256 bits long. Every hash value is unique. If two different inputs produce the same unique hash value, this is called a collision, and it makes the algorithm essentially useless. Last year, Google created a collision with the SHA-1 hashing algorithm to determine that it is vulnerable. SHA-1 was officially phased out in favor of SHA-2 in early 2016. Anyway, here's an example of hashing. Let's say you have a bunch of files you store on Google Drive. For each file, you generate the hash of that file and save those hashes to your laptop. Now, 3 months later, you go back to Google Drive and download all the files. You want to make sure that while they were there, they haven't been tampered with. So what do? You take the same hashing algorithm you used before and you rehash all the files. The outputs of that, the new hashes, should be identical to the old hashes that you saved onto your laptop. If anybody tampered with any of the files, the hash value of the files will be different. Tampering the file without changing the hash is impossible, assuming the hashing algorithm does not have any possible collisions. So just to visualize this, you have some plain text, you hash it, and then you have some hashed text. The hashed text cannot be unhashed as it is a one-way function, but the same plain text will always produce the same hashed value, assuming the hashing function is the same and there are no collisions. So hashing is used to verify that a given document or file has not been tampered with by comparing hashes before and after. Some more details about hashing. Security hashing algorithm is a family of hashing algorithms. SHA-2 and SHA-3 are both secure. SHA-1 is the one that Google found a collision in, so it's no longer considered usable. A common use case of hashing is that passwords are often stored as hashes. When a user creates a new password, the system calculates the hash for the password and then stores the hash in a database. Since the hash cannot be unhashed, even if some third party gets access to our user's database, they won't actually see the password. They'll only see the hash of the password. If they take that and log in with it, it won't work. When the user, who's the only one who knows their own password, authenticates by entering their credentials, the system calculates the hash of the entered password and then compares it with the stored hash. If it matches, that's a successful login. In this way, a user's actual password is never stored anywhere in the system. This helps ensure privacy and confidentiality. Another principle in information security is called salting, which pertains to password hashing. Essentially, it's adding a unique value to the end of each password so as to create a different hash value output. In doing so, you're hiding the password's real hash value by adding an additional bit of data to it to alter it, and then hashing it. Additionally, you're taking what could be common weak passwords, foobar123 or this is my password, and strengthening them with unique values that use suffix at the end. The unique value is called the salt, and it should be different for each password. So the same weak password used by multiple users will have different salts tacked on the end and will thus produce different hashes that are ultimately stored within your system. This adds a layer of security to the hashing process, specifically against dictionary attacks or brute force attacks in which a computer or a botnet attempts every possible combination of letters and numbers, or different combination of common words in a dictionary until a password is found. By adding a salt to the end of a password and then hashing it, you're essentially complicating the password cracking process. And again, it's especially useful in strengthening common passwords that users may use by adding unique strings to the end of them on their behalf. So, to recap the topics we covered the last few topics, encryption is a two-way function where information is scrambled, encrypted, in such a way that it can be unscrambled, decrypted later. Private Private key cryptography, symmetric encryption, uses a single private key to both encrypt and decrypt, whereas public key cryptography, asymmetric encryption, uses a public key to encrypt and another separate private key to decrypt. Hashing is a one-way function where data is mapped to a unique fixed-length value. Hashing is primarily used for authentication. Salting is an additional step during the hashing that adds an additional value to the end of the password that changes the hash value that is produced and stored. And that's the end of class number 3, the backend, and the end of the two-part series, the front end, the full stack developer. In this class, we covered the back end of the stack. We started with databases, both relational and non-relational, and then moved into the world of services, both monolithic and microservices architectures. We then moved on to another topic related to data itself, information security. We covered authentication and authorization, encryption, both symmetric and asymmetric, hashing, and salting. At this point, you should have a general idea of all the various parts of the stack and what they entail. In the next class, we're going to shift gears and get into the often mysterious and nebulous domain of the cloud. So until then, have a good one.